Welcome back to the deep dive. Before we jump in today, I want to just give you the headline, the one thing to hold on to.
A main takeaway.
Yeah, the core idea. We always think of our organs, the heart, the lungs, the liver, as the stars of the show.
Of course. They're the actors.
Exactly. But today, we're flipping that. The takeaway is this. None of those organs could work, or even really exist in the right way, without the empty spaces that were built for them first. We're talking about the architecture of nothing.
It sounds a bit philosophical, doesn't it?
Yeah.
But it's pure biology.
Right.
I mean, you can't put furniture in a room if you haven't built the room yet.
And that's it. Today is about how the body builds those rooms, the cavities that let the heart beat freely and the lungs, inflate.
It's the concept of making room for life.
Yes. So I want you, listening right now, to try and visualize your own body. Not the skin, not the muscles. Imagine the voids inside. That space in your chest for your heart, the pleural spaces for your lungs, the big abdominal cavity where everything coils. Without those carefully designed spaces, physiology just stops.
The nothingness is actually structure. It's a paradox. If the body were just a solid block of tissue, the heart couldn't expand to fill with blood.
The lungs couldn't draw in air.
It would all be useless.
Oh.
So today we're digging into the development of the intraembryonic coelom. That's the technical term for these early spaces.
And how they become the pericardial, pleural, and peritoneal cavities.
And of course, the absolute marvel of engineering that divides them all, the diaphragm.
And to guide us through this, because let's be real, embryology is a lot of folding and twisting that can kind of break your brain. We've got the titans on the desk.
We're synthesizing 3 major texts to really get the full picture.
We really need all 3 for this topic, I think.
Oh, absolutely. First up, we've got Langman's Medical Embryology. We're leaning on their chapter on the gut tube and the body cavities.
Langman is just brilliant for the mechanics, the pure logic of it all.
The engineering, the how.
Then we have Moore and Persaud's The Developing Human. And Moore is just, he's the master of the visual.
The metaphors. We're going to be talking about his horseshoe analogy a lot.
A lot. And of course, the deep clinical context. Moore is the one who really hammers home what happens when this elegant architecture fails.
And finally, we have I.B. Singh's Human Embryology.
Singh is so structured, very exam-oriented, which is helpful.
So helpful. He gives us the sequence, stage 1, then stage 2. Because everything in embryology is happening at once, and Singh lets us sort of pause the film and look at the individual frames.
Okay, quick disclaimer before we unzip this embryonic vest.
Good analogy.
We are putting these texts together to give you a mental framework. These books are the ultimate authority. So if you're a med student studying for boards or a resident reviewing hernia repair, please keep the actual texts open.
Yeah, think of this as the color commentary. We're trying to make the diagrams in the book come alive.
Our job is to spark curiosity, so you look at those diagrams and they finally click.
And maybe we should just briefly tease the clinical stakes here.
A good idea.
By the end of this, you will understand exactly how a newborn baby can be born with its stomach up in its chest, crushing its own heart.
Or why an ultrasound might show loops of intestine just floating nakedly in the amniotic fluid.
Terrifying images, but they become logical when you understand the embryology.
Okay, so let's do it. Let's unpack this. You have to start at the very beginning. The setup. We're in week 3, week 4.
The setup. This is where it all begins. The embryo is just a flat disc at this point, a little sandwich of 3 layers.
From 2D to 3D.
That's the whole game. And Langman describes this so well with his tube on a tube concept.
I love this visual. It just simplifies everything. So paint the picture for us. What are we looking at?
Okay, so imagine the embryo, but not as a person. It's just 2 tubes, one on top of the other.
Right.
On the dorsal side, the back. You have the neural tube. That's your future brain and spinal cord. And on the ventral side, the front, you have the gut tube made of endoderm. That's your esophagus, your stomach, your intestines.
So I have a back tube for nerves, a front tube for the gut, and in between them, holding it all together, is the mesoderm, the filling of the sandwich.
Exactly, the glue. But in the 3rd week, something really important happens to that glue. It doesn't stay solid.
If it stayed solid, we'd be that solid block of tissue we talked about.
We would. Instead, the lateral plate mesoderm, the stuff out on the sides, it splits.
It splits.
Yeah, think of a piece of Velcro being pulled apart. It delaminates into 2 separate sheets.
Okay.
One layer, the somatic or parietal layer that sticks to the ectoderm. That's your future body wall, the skin and muscle of your chest and abdomen.
And the other layer?
That's the splanchnic or visceral layer. It sticks to the gut tube. It becomes the muscular wall of your organs.
And the gap The space that opens up between those two sheets of Velcro.
That gap, that is the primitive body cavity, the intraembryonic coelom. It's the very first room in the house.
The space between the body wall and the organs.
Precisely.
So this space is opening up, but it isn't just a random bubble. This is where Moore and Persaud give us this incredible image that I think is the key to this whole stage.
The horseshoe.
The horseshoe.
It's the best mental map you can have. If you imagine you're floating above the embryo looking down at its back,
Yeah.
the cavity that forms is shaped exactly like a horseshoe.
Okay, let's trace it. Where's the curve of the U shape?
The curve is at the cranial end, head end.
Yeah.
And that curved space is the future pericardial cavity. It's the room that's waiting for the heart to develop.
Okay, so the heart gets the penthouse suite at the top. And what about the two long arms of the horseshoe running down the sides?
Those are the future pleural and peritoneal canals. They run all the way down toward the tail.
Yeah.
So at this very early stage, the space for your heart and the space for your intestines are all one continuous hallway.
Wow.
No doors, no walls yet, just one big U-shaped tunnel.
So the heart and the gut are roommates.
Briefly, yes. And Moore points out this really critical detail that often gets glossed over. The ends of the horseshoe, the limbs, they aren't sealed shut.
What do you mean?
They're open to the outside. They communicate with the extraembryonic coelom, the space outside the embryo itself.
Why? Why would you have a leak in the system? That seems counterintuitive.
It's not a leak, it's an escape hatch. It is brilliant engineering.
Okay.
Because later on, around week 6, the midgut, your small intestine, is going to grow so fast, so incredibly fast, that it literally won't fit inside the abdomen.
The physiological herniation.
Exactly. It has to pop out into the umbilical cord for a while. And if that connection to the outside space didn't exist, it would have nowhere to go. It would get crushed.
So the embryo builds a temporary extension onto the house because it knows the furniture is about to get way too big for the living room.
That is the perfect way to describe it. It's developmental foresight.
That's amazing. Okay, so we have our horseshoe, we have our split mesoderm, but the embryo is still mostly a flat disc. We need to close it up.
Time to make a body.
Which brings us to section 2, closing the vest.
This is all about embryonic folding. And you have two types happening at the same time. Lateral, side to side, and cephalocaudal, head to tail.
Let's start with the sides. I like the vest analogy here.
The vest works great. So imagine the embryo is putting on a puffy vest. The back of the vest is the neural tube.
Got it.
The sides of the vest are that somatic mesoderm, the body wall. As the embryo grows, the sides of the vest just wrap around to the front.
Yeah.
And they zip up right down the midline of the belly.
So as a zipper comes up, it's fusing the front body wall shut.
Perfectly. And as it zips, it pulls those two limbs of our horseshoe together.
Ah, so instead of two separate canals running down the sides.
They merge in the middle. They form one single large peritoneal cavity from the heart region all the way down to the pelvis. And the gut tube is now suspended right in the middle of it.
Hanging from the back wall like a chandelier.
Exactly.
That takes care of the sides, but there's also the head-to-tail folding. The embryo is curling up.
And this is a crucial move. I.B. Singh is really specific about this. It's hard to visualize, so stick with me.
Okay.
Initially, in that flat disc, the curve of the horseshoe, the heart cavity, is actually cranial to the developing brain. It's above the head.
That's so weird. The heart starts out above the brain.
It does. But as the head fold happens, imagine doing a forward somersault. The heart and its cavity swing 180 degrees, down and under.
So it tucks into the chest position we know.
Right. It settles into the thorax. But now we have a problem. Even though the heart is in the chest, it's still connected to the abdomen below it. There's no floor.
The open floor plans?
Totally open. The pericardial cavity, the heart space, connects to the abdominal cavity, the gut space, through two narrow corridors that run behind the heart.
And these are the famous coelomic ducts?
Or, full name, the pericardio-peritoneal canals.
Let's stick with the canals.
Good call. Think of them as hallways. At this point, you could drive a microscopic submarine from the fluid around the heart down one of these hallways on either side of the esophagus.
And you'd pop out in the abdomen next to the developing liver and stomach?
You would. And that is not ideal.
No. You generally don't want your heart and your liver sharing a space. The pressure dynamics are all wrong.
Completely wrong. The heart needs a low-friction, lubricated sac to beat in. The lungs need a vacuum to inflate. You can't have them all in one big bag.
Yeah, we need to partition the house, put up some drywall.
Exactly.
Which brings us to section 3, partitioning the chest. This feels like a turf war between the heart and the lungs.
It really is a turf war. Initially, the heart is king. It's taking up almost all the space. The lungs are just these tiny little buds branching off the gut tube.
But they're aggressive little buds.
Very aggressive. They start growing out sideways, laterally, and they expand right into those canals we just talked about.
They're invading the hallways.
They're expanding into the hallways, and as they get bigger, they push against the side body wall. Moore describes this really well. It's like pushing your fist into a memory foam mattress.
You see the sides bulge up around your hand.
Yes. Those bulges, those ridges, they get higher and higher until they form membranes, walls. These the pericardial membrane.
Okay, membranes, walls. But here's where it gets really cool for anatomy and where I.B. Singh's sequencing helps. There's important stuff trapped inside these forming walls.
Absolutely vital stuff. Buried inside these membranes are two things. The common cardinal veins, which are going to become your superior vena cava, the phrenic nerve.
The phrenic nerve. This is a huge aha moment for any med student who's been through gross anatomy.
It is. Because every year, students ask, why on earth is the phrenic nerve, which controls the diaphragm way down here, running right along the side of the heart sac up here? It's such a weird path.
It seems so exposed.
But embryologically, it's the only path that makes sense. Because these pericardial membranes, they eventually fuse in the middle and form the fibrous pericardium, the tough sac around the heart.
The nerve was in the wall became the heart sac.
And so now the nerve is stuck to the heart sac. The fibrous pericardium is the adult remnant of those embryonic membranes.
The nerve didn't wander there. The house was literally built around it.
That's it. It's not a detour. It's the original blueprint.
That makes so much more sense. Okay, so these membranes fuse, the heart gets sealed into its own room, the pericardial cavity, the lungs are in their own rooms on the sides, the pleural cavities.
The chest is sorted, horizontally anyway.
But we still have a huge opening. There's no floor between the chest and the abdomen.
We need to build the diaphragm.
The great divider. And this, section 4, I think is the most complex part of our deep dive. The diaphragm feels like it should be simple. It's just a sheet of muscle.
It should be, but it isn't. It's a Franken muscle. It is a composite structure.
That's the perfect term for it.
It's made from 4 completely different embryonic sources that all have to find each other and fuse perfectly. And if you look in Moore or Singh, they break these 4 down. You have to know them. If you don't know the parts, you can't understand the holes, the hernias.
Okay, let's list them. Component number 1.
The septum transversum. This is the big one. It's this thick plate of mesoderm that grows in between the developing heart and the liver.
I've heard it called a doorstep.
That's a great analogy. It grows from the front, the ventral side, toward the back. It forms a partial floor, but, and this is the key, it's incomplete. It doesn't make it all the way to the back wall.
It stops short.
It stops short, leaving those canals, those hallways, open in the back.
So we have a floor in the front of the room, but giant holes in the back corners. What does the septum transversum become in an adult?
It forms the central tendon of the diaphragm, that non-muscular white shiny bit in the middle.
Okay, part 1, check. We need to close those holes in the back. Component number 2.
The pleural-peritoneal membranes. These are the shutters. These are the membranes that grow out from the back body wall to close off those pericardial canals.
They grow forward to meet the septum transversum.
And fuse with it. And, spoiler alert, these are the troublemakers.
This is the weak link.
The absolute weak link. They're relatively thin. If these shutters don't close all the way, or if they don't get strong enough, you get a hole.
We'll come back to that. Component 3.
The dorsal mesentery of the esophagus. So this is the tissue that's already there, surrounding the gut tube in the midline. It just gets incorporated.
And it becomes what?
It forms the crura of the diaphragm, the 2 muscular legs that wrap around the aorta and esophagus as they pass through. It seals up the middle part.
Okay, and the last piece of the puzzle, component 4.
Muscular ingrowth from the body wall. This is the final step. As lungs keep getting bigger, they essentially burrow into the body wall, and they peel off an inner layer of muscle that gets contributed to the rim of the diaphragm.
So that forms the outer muscular part that actually contracts.
The part that moves when you breathe. So, to recap, septum transversum is the central tendon, pleuroperitoneal membranes are the shutters in the back, dorsal mesentery makes the crura, and the body wall gives it a muscular rim.
4 parts, 1 muscle.
And 1 nerve to rule them all. The phrenic.
Which brings us back to this crazy nerve path. Moore really connects the dots here. We know the diaphragm is down in the abdomen. But the nerve, C3, C4, C5, is from the neck. It's a huge commute.
It's a huge commute now, but it wasn't at the start. The diaphragm starts in the neck.
What?
In the 4th week of development, that septum transversum is forming way up in the cervical region, opposite the 3rd to 5th cervical somites.
So it's getting its nerve supply locally from its neighbors.
Exactly. But then as the embryo grows, especially as the spine lengthens and the head uncurls, the whole structure gets pushed down. It descends relative to the spine.
And it just drags the nerve with it.
Like a deep-sea diver dragging their air hose all the way to the bottom of the ocean. The nerve stays tethered to its origin, and that's why we have that mnemonic.
C345 keeps the diaphragm alive.
You'll never forget it.
And this explains referred pain. This is such a classic clinical pearl. You have a patient with, say, gallbladder irritation or gas under their diaphragm, and they complain of shoulder pain.
Yep. The brain gets a pain signal from the phrenic nerve, which plugs into the spinal cord at the C3-C5 level.
But C3-C5 also gets normal sensory information from the skin over the shoulder.
So the brain gets confused. It misinterprets the signal from the diaphragm as coming from the shoulder because that's where the wiring originated. It's an echo of our embryology.
That's just so cool. It shows how embryology isn't just history, it is living, breathing anatomy.
It really is.
Okay, let's move to section 5, the clinics. We've built the walls, we've built the floor. What happens when the construction goes wrong? Let's talk about congenital diaphragmatic hernia, CDH.
This is a really heavy topic, but it's one of the most direct clinical consequences of what we've been discussing.
So paint the picture, a clinical vignette.
Okay, you're called to the delivery room. A baby has just been born. It's blue, it's struggling to breathe. Severe respiratory distress. You look at its abdomen, and instead of being round and full like a normal baby's, it's flat, sunken in.
A scaphoid abdomen.
The scaphoid abdomen, because the abdominal organs aren't in the abdomen.
They're upstairs.
They're in the chest. You put your stethoscope on the left side of the chest, expecting to hear breath sounds, but instead you hear gurgling, bowel sounds.
And the heart sounds are pushed way over to the right.
Displaced. This is a classic Bachelec hernia.
A posterolateral defect. So this goes back to component number 2.
The pleuroperitoneal membranes, the shutters. It's a failure of one of those membranes to fuse with the septum transversum. It leaves a hole.
And since abdominal pressure is higher than chest pressure, everything just rushes up through that hole.
The stomach, the spleen, loops of intestine, they herniate into the chest. But here's the real tragedy of CDH, and Moore really emphasizes this. The problem isn't the hole.
Surgeons can fix a hole.
Surgeons are great at patching holes. The real life-threatening problem is pulmonary hypoplasia.
Underdeveloped lungs.
Remember our theme, making room for life. If the chest cavity is filled with intestines during the critical period of lung development, the lung on that side has no room to grow. It's physically compressed.
It stays tiny.
It stays tiny. The airways, the alveoli, the blood vessels, they never form properly. So even after you're born and a surgeon puts the bowel back and patches the hole, you can't easily fix a lung that was never built in the first place. That's what's so dangerous about it.
And Moore gives that stat something like 85 to 90% of these happen on the left side. Why the left?
It's a good question. The general consensus is the liver.
The liver?
The liver is huge in the fetus and it develops on the right side. So it acts as a big physical barrier. It essentially plugs the hole on the right, giving that pleural peritoneal membrane more time to close. It's a stopper.
The left side is just wide open. It doesn't have that protection.
It doesn't have that big bouncer at the door.
That makes a lot of sense. Are there other types?
There are. You can have a Morgagni hernia, which is much rarer, up behind the sternum. And then you have something called eventration.
Eventration is different because it's not a hole, is it?
Correct.
Yeah.
In eventration, the membrane closed, but the muscle never grew into it. So you're left with this thin, weak, membranous sheet.
So it balloons upwards.
Like a loose sail. It balloons up into the chest under abdominal pressure, but the organs are still contained. It's a pouch, not a free-for-all. So the symptoms are usually much milder.
And I saw that Moore also mentions a genetic link here, something on chromosome 15.
Yes, Geta-6. A reminder that this isn't always just a random mechanical fluke. Sometimes the genetic blueprint for closing that wall is flawed from the start.
It connects the molecular to the macroscopic. Okay, moving on. Section 6. We've talked about holes in the floor, the diaphragm. Now let's talk about holes in the front door, the ventral body wall.
Gastronesis versus omphalocele.
A classic board exam question.
And Langman does a fantastic job differentiating these. They can look similar at first glance, bowel, outside the body, but their embryological cause is completely different.
Okay, let's start with omphalocele.
So remember the physiological herniation. The gut pops out into the umbilical cord for a while.
Right, and it's supposed to come back in around week 10.
In an omphalocele, it fails to return. And the key visual here, the most important thing, is the covering. Because it's still inside the umbilical cord, the herniated bowel is covered by a protective sac, a membrane made of amnion and peritoneum.
So the memory anchor I always use is omphalocele has a seal.
That's perfect. Omphalocele has a seal. It looks like this shiny, grayish bubble coming out of the belly button. And because it's a failure of a fundamental developmental process, it is often associated with other major problems.
Like chromosomal abnormalities, heart defects.
Exactly. It's often part of a bigger syndrome.
Okay, now contrast that with gastroschisis.
Gastroschisis is a totally different problem. This is a failure of the body wall itself to close. A structural defect, usually from that lateral folding we talked about at the very beginning.
And it creates a hole, usually to the right of the umbilicus.
Right. And the appearance is dramatically different. The bowel is naked.
No seal.
No seal. It's just floating freely in the amniotic fluid. It looks raw, angry, messy.
So my mnemonic for that one is gastroschisis is a split.
Split in the wall. That works. And because that bowel has been bathing in amniotic fluid, which contains fetal waste, it gets very irritated and damaged.
Inflamed and matted.
Right. So these babies can have long-term gut problems.
Yeah.
But here's the twist. Gastroschisis is less likely to be associated with other genetic syndromes. It's often just a one-off plumbing accident.
So, to summarize, omphalocele is sealed. It's a failure to return, often syndromic. Gastroschisis is a split in the wall. It's naked bowel, and it's usually an isolated defect.
That is the perfect summary. That distinction is critical.
Okay, we are in the final stretch. Section 7. This is where we go deep into the abdomen to talk about mesenteries and the lesser sac. This is where my eyes used to glaze over in the textbook.
A lot of people's do. It's abstract origami. But let's try to make it logical.
Please.
First, a simple definition. A mesentery is just a double layer of peritoneum. Imagine a balloon is the peritoneum, and you push your fist, an organ, into it. The two layers of balloon that wrap around your wrist on the way back to the wall. That's the mesentery. It's the sling that holds the organ and carries its blood vessels and nerves.
So they don't get tangled. And we start with two of them, a dorsal and a ventral one.
The dorsal mesentery is the big one. It runs the whole length of the gut tube, suspending it from the back wall. The ventral mesentery is special. It only exists up at the foreguts, the stomach and liver area.
And it comes from the septum transversum.
It does. It's just the part of the septum transversum that thins out. And it becomes the lesser omentum and the falciform ligament in the adult.
But the real mind bender here is the lesser sac, the omental bursa.
The hidden room.
The hidden room behind the stomach. How on earth does that get there?
It's a dance, a rotation.
Wow.
As the stomach grows, it's not static. It spins 90 degrees clockwise on its long axis.
Okay.
And as it spins, it pulls its mesenteries with it. It pulls the dorsal mesentery, the one behind it, over to the left. And it pushes the ventral mesentery to the right.
It's like wrapping yourself in a blanket. If you stand and spin, the blanket wraps around you.
That is the perfect analogy. And just like wrapping a blanket creates folds and pockets, this rotation of the stomach traps a pocketed space behind it. That trapped space is the lesser sac.
And it's not completely sealed off. Is there a doorway?
There is. A little one. The epiploic foramen, or the foramen of Winslow. It's the communication between that hidden back room and the main abdominal cavity, the greater sac.
Why does a surgeon care about a hidden room behind the stomach?
Oh, a couple of big reasons. One, fluid from a perforated ulcer or pancreatitis can get trapped in there. But two, and this is life-saving, is the Pringle maneuver.
Ah.
In a major liver trauma, if the liver is bleeding everywhere, a surgeon can stick their finger into that foramen, that little doorway, and pinch the structures running right in front of it, the hepatic artery and the portal vein.
And cut off the blood supply to the liver.
It's a biological tourniquet, and you find it by finding that empty space. The embryology creates the surgical landmark.
So the void isn't a void. It's a result of the stomach twisting, pulling the wallpaper with it, and creating a critical access point.
Beautifully put. History creates anatomy.
We have covered so much ground today. From a flat disc to a tube, a horseshoe, to a partitioned house.
We built a Frankenmuscle diaphragm from 4 different pieces.
And watched the stomach do a pirouette to create a hidden room.
It really is an engineering masterpiece. And I think if there's one theme from all 3 of these sources, Langman, Moore, and Singh, it's that this incredible complexity arises from a few simple mechanical rules.
Fold here, fuse there, rotate this.
But if one of those steps is missed, like a pleuroperitoneal membrane failing to fuse, the consequences are just devastating.
It brings us right back to that opening thought, making room for life.
Absolutely. We always think of biology as growth, more cells, bigger organs, but embryology is just as much about constraint, about partitioning. Creating the empty space for the lung is just as important as creating the lung cell itself.
If the space isn't there,
The potential is lost. The organ can't become what it's meant to be.
space creates potential. I love that. That's a great philosophy for life, not just embryology.
It really is.
For those of you listening, if you want to see the color-coded map of that diaphragm, I really recommend it. Check out figure 8 to 7 in More or figure 17.5 in IB Singh. It makes the four components just crystal clear.
Oh, absolutely. Once you see it color-coded, you will never forget it.
Thank you for diving so deep with us into the hidden architecture of the body. It really changes how you look at a simple chest x-ray, doesn't it?
It changes everything.
Until next time, keep making space for knowledge.